So you guys are in operational tips for deploying Spark. My name is Miklos Christine. I'm a solutions engineer at Databricks. I help customers deploy Spark in our environment. And let's see, who am I? I was previously at Cloudera. I was in the support org and the sales organization helping deploy big data solutions, typically on-premise for them. So I have pretty deep knowledge of the big data stack. I worked with HBase, Hive, Impala, Spark as well while I was there. I would consider myself a Apache Spark expert and solutions engineer at Databricks now. So a quick agenda of what we're going to go over today. Quick overview of Apache Spark, configuration systems, what to look for when you're doing configurations for these systems. There are a lot of them. Pipeline best practices, and then debugging techniques. So I'm pretty sure everyone knows what Apache Spark is by now. This is a quick picture of what your application would look like on a distributed platform. This is just a view of a single application. It's broken down into jobs, and those jobs have tasks that are run on executors. And then in terms of Spark configurations, this is kind of the Spark landscape. You have the Spark core APIs, the SQL data frames APIs, as well as streaming and other frameworks that are built on top. Each one of these has its own set of configuration parameters that, as an application developer, if someone using Spark, you should know about some of these parameters. Some of them are going to be set up for you by your DevOps team or data engineering team who are helping you deploy your Spark applications or clusters. But for some people, you might not know what those configurations are. So I'll kind of go into how, as a support person who is helping people deploy these applications, what do I do, kind of tips and tricks of what do I look for when I'm trying to understand a user's platform. So in the basics of core configurations, what do you have available? And a lot of people know that there's kind of two command line options or files where you would define configurations, and that's sparkdefaults.conf. And in a Spark project, we have a template of what those configurations are, and you can set your own. The sparkn.sh is more JVM level, setting up memory configurations, maybe GC logging. It's more the JVM parameters that you would set for these applications. And so those are two of the main ones that, depending on how you're deploying your application, you would put those configuration properties in. For your applications, you actually see when you're going through tutorials and walkthroughs, you can also set these programmatically, and that's with the Spark conf. And then additionally, there's also some Hadoop-related configs. So if you have a Hadoop system, Spark is compiled against the Hadoop version, and some of those configurations are placed typically in these types of files where if you had an existing system running on Yarn, you would copy the core site and HDFS site into the configuration of where your Spark application is going to pick up those configurations in that same directory and read those configurations in. And so some common things that I do when I'm looking at a system and trying to debug issues is trying to understand what's currently set. And so there's a few things you can do within the environment. And it's typically if you have a shell or a REPL open, you can call the spark context.getConf. And there's an API called toDebugString. That's going to print out all the non-debug or non-default parameters for the application. You can kind of review what's being set for you. And so you can compare, are these set to the defaults? Are these things that I need to take into consideration? Later on, we'll go into how these tie into looking at your application and maybe things you need to tune when you're running Spark SQL joins or aggregations and things like that. And then there's also the Hadoop-related configs where it's not in the Spark configs per se, but there's also another API where you can get an iterator and print over those and making sure that those are set. And so that for those configurations, there might be compression codecs that you need to set that you want available to you. I think LZO is one of them you would have to set in these configurations in one of the core sites or HDFS sites. And so making sure that those are set when you're in that environment, this is one way to verify that. And then Spark SQL configurations, there's a few ways to do it. You can, in this example here, there's this syntax where you can do set key equals value, and below is an example of how you would set that within this SQL context. If you already have that environment running, essentially you can run that SQL statement where it's set the property name and value, and then below you can verify all the SQL context properties, very similar to how we were defining it previously. So you can verify that you've actually set the property now. So next we'll go into pipeline design, kind of what do you look for in terms of file formats, how they affect your performance when you're running these applications, compression codecs, Spark APIs, when to use the internal Spark APIs, when to write your own, and then job profiles, what to look for when I'm typically debugging these applications for users, right? If you come to me and say, my Spark application is slow, where am I gonna go look first, and how do I think about that process, right? So file formats. Typically, a lot of the users that I'm working with come with data sets that are in CSV or JSON, and these are text-based file formats where we can read them in, there's APIs to do that, but is that an efficient way to be processing your data? And typically not, right? And that's why there's always, you hear ETL, right? You want to ETL your data sets into a more efficient format, right? And so some people have data sets that are coming in as Avro, but typically what we're seeing for performance is you write your data sets into a Parquet columnar format. And here, these images are kind of representations of how these data sets are stored on a file, on disk, actually. And this is kind of the first step of when you're building out an application, you should make sure that your data format is in a proper format. So the image on the left, the table format, is typically what you would see in a CSV file, for example. You see that you have columns delimited maybe by a comma or a pipe, and you're gonna have to do text processing of that, right? You're gonna find that delimiter, that's gonna be your first value, and then you keep going through that, right? And that's the processing underneath that's being done when you have just a text format. But with these other two formats, you have a schema associated with it, and it's written in a serialized format, right? So it's a little more efficient, and for the columnar format, it's even more efficient because the columns, as you see, A1, A2, A3, are grouped together, and they have the same data types. So you can do special tricks, special encodings that can make them more compressed, and also you can skip groups fast through the file, because if you're not using that column, now we can go to the offset and just read the column data that you need, instead of having to scan through the file to find the columns that you need, right? And so you can see the differences between those two in these images. Next is choosing a compression codec. This is something that's also good to test out in your platform. And a few of the popular ones are Snappy, gzip, and LZO. And this one you should really test out with your data sets and some workloads and choose one that works best for you. I've seen a variety of customers. Some of them choose Snappy, some choose gzip, just depending on your data sets and how they're and how you're processing them. Those just perform better for them. And a few of the configuration parameters that you should look into are the I/O compression codecs, which, going back to those configurations we were looking at, typically live in like a core site or HDFS site, and that determines what's available to you in your system. And if you have DevOps teams building out these systems for you, they're setting that up for you, and those configurations are configured for you there. In terms of Spark SQL, and when you're writing out Parquet, there's a specific config param that you can set in the Spark SQL config, where you can say set Spark SQL Parquet compression codecs to gzip or Snappy or LZO, whatever you want to test out and use for that environment. And then the last one, typically you don't need to use when you're writing out these files, is for the intermediate data, where I believe there's a special default that's already configured for you. And typically you don't need to modify the last one. And the first two are what you really mainly need to be looking at in testing. So the small files problem still exists. And that's kind of an issue with a lot of the Hadoop traditional file systems that people were running last couple of years. And what that means is you don't want to create a lot of small files, because there's metadata associated with that. If you're listing a directory with 100,000 files is going to take some time. And so even that is a problem when you're working in these environments, right? Listing out all the data, all the files that are there so that you can actually go read the data sets, right? You need to know what the files are there so you can actually read them. So making sure that when you're writing the files, you're not also creating a lot of small files. And here, the display is a data set that I was working on where I figured out what the size in bytes were, and I was analyzing how big are these files actually. And so from here, I was looking at this, and now I can use coalesce to write out less number of files, but that are bigger. And typically what you want to do is create maybe files that are 100 megs to 200 megs in that range, and then test the performance of that for your queries, right? And so you want to do that throughout the tables that you're writing. And so this is part of the data processing for your pipeline and getting your data in the right format and the right sizes so that it's efficiently processing these. And typically in Spark, you would have one core probably reading through each one of these files. So understanding the number of cores that you have on your system and how it's interacting with your data is also important. The next thing about part of the pipeline that I think is somewhat confusing is related to partitioning. And so partitioning, there's a few different levels of partitioning that occur in Spark. And one of them is in terms of the data frame and RDD data abstraction that we have. And so Spark has a number of partitions that you can either query. And here is an example of calling the get number of partitions within PySpark. And you can see that this is going to determine the number of file writers that you have when you're writing these data pipelines, right? And so this is important when you're using coalesce. That's going to reduce the number of partitions for that data frame that you have that's representing your data that's partitioned across the executors. That's the Spark level partitioning. The next one is the table level partitioning, which is a notion that comes from Hive, but it's very similar. Spark uses the same kind of framework where if you partition for a particular column, we're going to create directories for each value in that column. And then within there, we're going to store the rest of the data. And so you still have the whole data set within a root directory. But the benefit here is if I were searching for a particular year in this example, you can see that all the year data is, all the years are broken up into 2014 and 2015. And the data sets are split between those two directories. Now, if I were to do a select query from this table where year equals 2014, I'm only going to scan the data that's in 2014. So you're efficiently processing and reading the data sets only when you need it. So this is called partition pruning. And so understanding these two things and how they relate. Now, if you were to reduce the number of partitions in Spark, that's going to create the number of files that are written in each one of those partitions. And so they are related, but they're two different concepts that you should know about when you're designing your pipeline and processing it. And so this can be your data engineers, they're designing these, they're setting up the data sets for data analysts to use, and this is something that they need to consider. Now, how do you profile the Spark jobs? And what I typically do is use the Spark UI, and it sounds pretty high level, or it sounds like it's not the most efficient way, but it gives you a quick understanding at a high level of what's going on in your job. And they have these DAGs that are available, and you can see the different stages that your jobs are going into, and whether it's an aggregation or a projection. They give you a lot of information on what's actually going on in each stage of the job. And for SQL, it's got a really nice UI where it breaks down the job into each one of these nice little boxes where it tells you whether it's a filter operation or a sort operation or a join operation, which is occurring on the bottom. And for this query, I can go and profile whether it's doing things efficiently, where I'm filtering out data sets efficiently, how many records are actually being filtered out, and how many records I'm actually joining at the very bottom. And so this will give me an overview of what the user actually wants to do and how much data is associated with it. Because if I was just looking at the query, I'm not going to know this information. I don't know that information about the data set. At least this gives me the metrics that I can use to start thinking about what's next, where do I need to go next to look at why this job or why this query is not performing optimally. And streaming, Spark Streaming also has a great UI that shows you the input rate, how long the scheduling delay is, and a lot of other good information when I'm typically profiling and analyzing these jobs. So within the UI, there's also a lot of additional metrics that tell you whether the job is actually being distributed across your cluster efficiently, right? And here, this is a 12 executor cluster where I can see the total task time, total failed tasks that are being run, as well as how much input data is being read across the executors. And I can see if there's skewed data sets, right? Is the data in the right format? Have we done what I talked about previously in this example, right? And from here, I saw this was, again, the same example that I was using where I've efficiently written out the data sets across in the Parquet files. And they're all about the same size. And it's reading those data sets in parallel in an efficient manner. And it's also not shuffling a lot of the data as well. So that's not a problem. And this would help you see if maybe you have a skewed key within your SQL query. Maybe that's going to be shown within the metrics on this page. And this is an aggregated metric per executor. Going down one more level, you can see the task metrics and analyze whether a particular task is garbage collecting or a particular task has an error. And so within the UI, again, you can drill into these sections and figure out which tasks are failing within your job and where the problem is. And so this helps you get more information about the distributed nature of the platform, right? Is one executor garbage collecting more heavily than the other? This is where you're going to get that information. You're going to have the host name and IP of those instances. And then that can help you drill into, maybe I need to go look at the GC logs. Maybe that executor doesn't have the right GC logging options for its JVM, right? So it help you think about a few other things that you can look into for this environment. Going into monitoring for these platforms, right? There's a few different ways you can do it. You can go use Graphite and Ganglia, and typically there's templates to do this, and there's a lot of documentation on the web for people who've done this already. And there's a link that when these slides are posted, you can go to that the Hammer Lab goes over how do you set up Graphite and Grafana to kind of profile your jobs using the metrics that are built in. And they're very good metrics in terms of how they tell you about what's occurring on the cluster today. So you can see the number of active tasks stacked per executor. You can also see the completed task per executor, and that in a time series display, as well as the number of completed tasks per minute per executor. So when going through these debugging steps, I typically go through and make sure that when a user says that their jobs are failing or their jobs are really slow, I make sure that I go through these 3 steps first. Typically analyze the driver stack traces. So drivers log4j or standard error, standard out logs. Review those and make sure there's no obvious stack traces that you have a class not found exception or maybe an out of memory error for the driver, right? There's these obvious errors that you can look for in those logs for the driver. If that's not the problem, then maybe it's an executor issue. So I drill into the executors and figure out, are there any outstanding error messages there? And typically, if there's a task failure, tasks are rescheduled and retried up to n number of times. So you might have to go drill into when was the first executor that failed, which was the first task, and why, instead of finding just one of them, right? You're making sure that you find the root cause of what caused that failure, as well as removing the metrics. So making sure you don't have an out-of-memory issue, disk errors, maybe you're spilling the disk too much and filling up the local disk, which is what caused the executor to fail, as well as maybe you don't have intermittent network issues where you have no route to host issues. Maybe you had a DNS issue, right? And a lot of the support issues that we run into are the following, right? Sometimes we're getting out-of-memory issues for the drivers, where if a user is using Spark, they might call collect on a data frame thinking that it wouldn't cause a problem. And if you pull all that data set to the driver, you're going to cause the driver to go to hit an out-of-memory issue, right? Because collect is going to pull the distributed data set into a single JVM, which then isn't very efficient for the process. As well as another issue is out-of-memory errors for executors, which can be caused by skewed keys, maybe not enough partitions within your Spark data frame when you're doing a join operation, and things like that. Out-of-disk space issues, again, maybe you're shuffling a lot of data and you haven't provisioned enough disk space for those data sets, right? So monitoring the disks of your executors is also important, right? It's not everything is done in memory. You're going to be spilling to disk, and so disk is also important when you're running these distributed frameworks. And long GC pauses, making sure you have the right GC options for all your JVMs, right? You should not have no GC options. There should be some options for you to efficiently do garbage collection, right? Because it is a JVM process, and they should have those options. And then making use of the right APIs. So a lot of some performance issues that we run into were just users trying to write their own APIs or user-defined functions and not calling the right APIs that are already built into the framework, right? So I'll go into it in the next slide. There's a lot of functions that are already built into Spark that you should be leveraging. And there's great documentation that I've linked to the bottom that I usually point people to, where if you have a UDF, don't try to write these using the native language that's already, that you're currently using, like Scala or Python. If there's already a built-in function that's compiled into the JVM for you, that's already running, because it's going to be faster to use these built-ins or even chain these built-ins to achieve what you want to do, right? So some examples are there's a toDate function where if you have a string, you can pull out the date of that string in timestamp value or a column and generate just the date column. Regex replace or regex extract is the last one. That's another one. You don't need to be writing those. There's already built-in functions available for you that are going to be the fastest way to run those actions on your data frames. And then also get JSON object, right? And so these are popular ones that people have been using, but there's a huge set of them that if you have to do these operations, there's no need to write these UDFs yourself and register them. You can just import these and then start running them yourself. Another thing we see a lot of issues for SQL joins. Understanding the query plan that's being generated. Earlier, we were looking at the query plan that was in that nice UI, and you see all metrics on the number of rows and the number of operations that are done to generate your query. And that's actually after the run. But you can actually inspect it before you run the queries using this explain. That will show you the operations that are going to be done. You can see if you're efficiently doing predicate pushdown, if you have where clauses within your query. You can see that in the plan. And so you can kind of get an understanding of whether you're writing an efficient plan for your query or not in using the explain operation. There's another one where there's a good forum post on our forums where if you want to cache maybe a small reference table and do a partition join, there's actually a threshold that you can set within SQL. There's an auto broadcast join threshold that you might want to adjust so that you can make sure that you're doing a partition join instead of a broadcast join. Maybe that's the problem that your queries are having. The next one is Parquet, related to Parquet and external systems. If you have Hive or some other external system writing your Parquet data, there's this flag where what the symptoms are if you try to read a Parquet data in your environment, the string columns are going to be represented in a weird format. You might think that there's a bug or maybe the Parquet file is corrupt, but there's this property that you can set binary as string where some systems that write this out, like Hive, have this set to false while other systems have it true. So making sure that the issue isn't just a configuration issue within your system, and you can use those tips that I showed earlier to make sure that what value this property is actually set to. And then also, when you're doing shuffle joins, making sure that the number of partitions is tuned appropriately. And so some users need to tune this property when they have large joins and they want to split up the join on more partitions. And that's the end of my talk. So thank you. So we have a few minutes for questions, if anyone has any.
So earlier you mentioned that when you coalesce RDDs and data frames, it should be in the 100 to 200 megabyte range. I was just wondering if there's like a good way to dynamically choose the size of the coalesce. And I was just curious if that 100 to 2 megabyte range is the same for uncompressed and compressed Parquet files.
Great question. So I think, is there a way to manage it initially while you're writing it dynamically? There's no simple way to do it today. You actually have to analyze the data first and then write it out and maybe do some testing beforehand and figure that out. So there's no easy way to do it today, actually. So that's the first answer. The second question is it compressed or not? Those numbers I was giving are compressed. So those are data sets that I tested out that I was getting good performance with, compressed data. You had a question over here.
You showed us some advice on garbage collection. Can you dig a little deeper into that, like give some good cases for how to adjust the garbage collection?
Yeah, so for the most part, a lot of the tools that maybe are being used today to manage these typically have good defaults. I don't remember if the Spark templates that are already available in the code base already have them. I believe they do. So if you just use those, the templates, and look at the properties that are set there, those should be good enough. You shouldn't have to be tuning the garbage collection params too much. Like not everyone should have their own custom settings. There's a general purpose like default that should get most people through it. But if it's garbage collecting too much, it doesn't mean that you just need to tune your garbage collection parameters even more. You should probably look at your job workflow, make sure the number of partitions are defined appropriately, that if you had skewed data sets, maybe you want to add more partitions and repartition to a higher number, so you're splitting up those tasks more in parallel.
So in the production deployments you've seen, were the Spark clusters main daemons being kicked off on the data nodes of, let's say it's a HDFS cluster? Are the Spark running on the data nodes itself, or were they dedicated separate cluster nodes for Spark?
So typically, at Databricks, we don't have HDFS, like we run in the cloud. But for those other cases that I've seen, they're run on node managers that are governed by Yarn, and those run on top of the data nodes. So it's not a separate cluster.
Whenever we do a lot of runs, everything runs fine, but suddenly when we move into ML pipelines with random forest models, the system starts behaving very strangely. And we get a lot of out-of-memory errors. Do you have any specific advice for that, to avoid that? We played around with some of the settings, like let's say the size of the executors and so on, but it didn't change a lot.
What mode are you running in? Are you running on Yarn, Mesos?
Yarn.
Yarn? So the most typical case with Yarn is the out-of-memory. There's a memory overhead. There's two properties. There's like an executor memory overhead and a driver memory overhead. So if you're increasing the executor size, you also need to increase the memory overhead. And so I've seen those were a majority of the issues in the past, but then I'm not sure if that's going to solve your case. Maybe you've already modified those configurations, but that's the most common case. Otherwise, I would need to kind of dig into your environment. Sorry. I think last question, and then
Yeah.
There's a config value called speculation, where a slow task detected, it will start another one, right? So how that slow task is determined?
slowed. Great question. I'd have to look at the code and figure out what determines that threshold of when we want to speculatively start another task. I don't know off the top of my head. Yeah. But yeah, that is a property that you can set, and that would determine.
All right, let's have one last round of applause for Miklos.